Lesson 8, Calculus AB using a textbook by Larson. We're on Chapter 1, Section 5, Infinite Limits. All right, so the goals here with infinite limits are to determine infinite limits from the left and from the right. Find and sketch the vertical asymptotes of the graph of a function. Determining infinite limits from a graph. Determine whether f of x approaches infinity or negative infinity as x approaches negative 2 from the left and from the right. So that's a negative 2. So we're supposed to figure out the limit as x approaches negative 2 from the left and the limit as x approaches negative 2 from the right of f of x. And they got a picture for us, which was nice of them. We don't have to draw it ourselves or look it up. So as it comes in from the right, it is going up boundlessly to infinity. And as it comes in from the left, it is going down to negative infinity. And that's all you have to do. You just have to look at the graph and see where it's going. Okay, and so then the next one down here is the secant of pi x over 4, and they gave us a graph again, which is, again, very nice of them. So we're finding the limit as x approaches negative 2 from the right and from the left of f of x. Okay, so from the right, here's negative 2. So coming from the right, it's going up to infinity again. And then from the left, you can see it's going down to negative infinity. All right. Next up, numerical and graphical analysis. Create a table of values for the function and use the result to determine whether f of x approaches infinity or negative infinity as x approaches negative 3 from the left and from the right. Use a graphing utility to confirm your answer. All right, so the directions said that they want to have you make a table. So we have to make a table. So we're going to approach negative 3 from the left and the right. Oh, by the way, there's a thunderstorm going on outside. So if you hear big banging noises, that's what it is. Okay, so we want to find the limit as x approaches negative 3 from the left and the limit as x approaches negative 3 from the right of f of x. And again, they wanted us to use a table. So if we use a table, plug in values of x, all right, it helps sometimes for people to draw a number line. So the number is negative 3, there is 0. So coming in from the right, which is what's down here, from the right, getting closer and closer to negative 3, when you get really close to it, it's like negative 2.9. And then even closer, negative 2.99. And even closer than that is negative 2.99. 9. Just keep adding 9s on it. And then it wants to know, I'm hoping I use the same numbers. I'm checking. It'd be a sad story if I didn't. Oh, I did. Life is good. All right. So, and then coming in from the other side, from the left, coming in this way, so as it gets really super small, it's getting close to the number negative 3. But it comes in that way, you're getting closer, to negative 4 going over here. So it's going to be negative 3.1, 3.2, 3.9, all the way up to the negative 4. So when it's really close, it's maybe negative 3.1. And then even closer, negative 3.09. And then closer yet, negative 3.001. Let's use negative 3.01 there. So negative 3.1, negative 3.01. So anyway, let's put in our calculator. Oh, let me get my better calculator. All right. So they wanted us to use a table, and I would agree. It's a lot less painful just to graph it, but they didn't say to do that. So we have to, we can confirm it with a graph. So it's x divided by x squared minus 9. So it's going to have asymptotes at 3 and -3 because that's where the denominator is undefined at. It'd make it 0. So at -3, you can see as it's coming in from the right, it's going to infinity, and as it's coming in from the left, it's going to -infinity. All right, and now that I have it in there, I can just go second, calculate the value. And so the value, when it's -3.1, you get -5.1, and then second, calculate the value. When you put in -3.01, you get -50.1, and then second, calculate the value. When we put in -3.001, we get -500. So you can see it just keeps getting bigger and bigger. So as it approaches -3 from the left, it's going to -infinity. Well, -3, let's see, -3.1, -3.01. So that's coming in from the left, which is that one. And on the graph here, when it was coming in from the left, it was going down to -infinity, which, yeah, so -infinity, because it was getting really small. And if you plug these numbers in the calculator, -2.9, you get 4.9, and then 49.9, and then 499.9. So it's increasing, and it's going to positive infinity, which is what we saw on the graph. As it comes in from the right to the number -3, it's going up to positive infinity. Okay, same thing down here with the tangent. So they want you to find the limit as x approaches -3 from the left, and the limit as x approaches -3 from the right for f of x. So I'm just going to reuse my same tables from up there. So we had -3.1, -3.01, -3.001, and then here I had -2.9, -2.99, -2.999. All right, so putting that in our calculator, don't forget to put parentheses around the top. So let's see, go up to y equals. So we're going to do the tangent, extra set of parentheses of pi x divided by 6, close the parenthesis. I'm going to put the zoom on trig because we're graphing a trig function. And again, when you graph a trig function, it counts by pi over 2. So you can see here at pi, it's going up to infinity, and over here at this pi down here, it's going down to -infinity. But actually, you know what? That isn't pi. It's counting by 1 because of the fact that it divided by 6, pi x over 6. So it had pi over 6 is the b value on it. So knowing that that's the b value, for tangent, the period of it is pi over b because it repeats every pi. And here the b is pi over 6. So pi divided by pi over 6. And you get the number 6 out of that. So actually, this is actually at -3, and that's at +3, because the period of it's 6. And so 3 this way and 3 that way to give a full period of it. All right. So as it approaches -3 from the left, this would be from the left. So -3 from the left, it's going up to positive infinity. And as it approaches -3 over here from the right, coming in from the right, it's going down to -infinity. So when we put the numbers in the calculator here, second, calculate the value of -3.1, we get 19.08 or 19.1. Do it again for the next one, -3.01. You get 190.98, and if you do the next one, you get 1909. And these numbers, when you plug them in, -19.08, -190.9, and then -1009. So this one is going to positive infinity, and this one's going to negative infinity. which we confirmed on the graph. When it comes in from the left, it's going to positive infinity. When it comes in from the right, it's going down to negative infinity at -3. You could also trace it if you don't know where the numbers are at. So there you can see -3. It's coming down. So if you take it to the right, it's going up to bigger and bigger numbers. And then it jumped over and it's coming back down. But you can see that that's where the -3 is at. All right. Next one. It says finding vertical asymptotes. Find the vertical asymptotes, if any, on the graph of the function. So recall that the vertical asymptotes are where the graph is undefined in the denominator. So on this one, all right. So on this one, the vertical asymptote would be at 3 because you set whatever is in the denominator equal to 0 and it's to the third. So since it's to the third, it's going to make 3 minus 3 is 0. So when x is equal to 3, it's got a vertical asymptote. You could confirm it by graphing it on the calculator if you wanted to. This one's not going to have a vertical asymptote because when you set it equal to 0, it's equal to -9, and that's not possible at all. So there's no vertical asymptote. And then on 26, this one's fun. To solve this one, because there's 4 terms in the denominator, it's a factor by grouping problem. So what you're doing is you're factoring out x squared. And then from the second half, factor out a -1. And then, since both of them have an x plus 3, you can factor x plus 3 out, which leaves behind then x squared minus 1. And then it keeps going because that factors. And that factors into x plus 1 and x minus 1. And the top here factors into x plus 3 and x minus 3. All right, so there's going to be a hole at x equal to -3 because it canceled out. So a removable discontinuity at the number -3. And then at 1 and -1, there's going to be vertical asymptotes. And so at 1 and -1, there's discontinuities. Oh, can't say it. But it's at both of those, it's discontinuous. And it has vertical asymptotes. And then if you wanted to overachieve on it, we could talk about the horizontal asymptotes. Remember, you look at the highest power on the top and the bottom. The highest power on the top is x squared, and on the bottom x cubed, so that makes 1 over x. So y equals, as x goes to infinity, 1 over infinity, which is 0. So y equals 0 would be the horizontal asymptote. 32, same question. They want to know where the vertical asymptotes are at. And so what would make this look better if we change tangent to what tangent is, and tangent is sine over cosine. And then cleaning it up some more, I'm going to multiply the top and bottom by 1 over that omega, so that makes that then sine theta, oh it's a theta, and then over theta times cosine theta. I can't always remember my Greek letters or whatever those are. All right, and so they wanted to know where the vertical asymptotes are. Again, that's where the denominator is equal to 0, so that's when theta is equal to 0, which would be just 0, where cosine theta is equal to 0, and cosine is equal to 0 at pi over 2, and then at 3 pi over 2. So notice that's 1 pi more. So every pi, it's going to repeat and be a 0. So the final answer on it would be theta equal to 0 and pi over 2 plus k pi, where k is an element of integers, z. Okay, on 34, it says, Determine whether the graph of the function has a vertical asymptote or removable discontinuity at x equal to -1. Graph the function using a graphing utility to confirm your answer. Okay, so on 34, this factors into x minus 4 times x plus 2. So this does not cancel out at all, so it's not removable because it doesn't cancel out. So it's got a vertical asymptote at x equals -1. And if you graphed it, you would see it's got a fun slant asymptote going, also an oblique asymptote, whatever your favorite thing is for that. Again, this is overachieving now. This is more than we had to do. But if you were to look at what y is equal for the horizontal asymptote, the highest power on the top is x squared. On the bottom, it's x. So it's one more on the top than the bottom, and that means it's got a horizontal, it's got a slant asymptote. And again, some people call that oblique. I'm finding they're called both. So just keep that in mind if somebody says one word or the other. So remember, to do that, what you do is you divide the denominator into the numerator. So it goes in x times, subtract, that makes -3x minus 8, then minus 3, subtract, and you get -8 minus -3 makes -5. Remember, we don't really even care about the remainder, we care about that. That is the slant or oblique asymptote. All right, more than we had to do. All we had to really do is come up with the fact that x was equal to -1. But if you wanted to look at it on the calculator here, remember, put parentheses around the top and parentheses around the bottom, else it's not going to graph that. So let's see here. We got parentheses x squared minus 2x minus 8 parentheses divided by parentheses x plus 1 graph. Oh, I think it's on trig still. Let me fix it. So zoom, standard. Okay, so you can see that slant asymptote at y equals x minus 3. It goes through the -3 and then with a slope of 1. I'll draw it. All right. So we got a vertical asymptote at x equal -1. And we got an oblique asymptote at x minus 3. So go down -3, up 1 over 1. So there is y equals x minus 3. And it came in really close to it over here. And then over here is what the picture is right there. All right. 36 is best done just by graphing it. So let's go ahead and graph it. So y equals sine of x plus 1 divided by parentheses x plus 1 graph. And I need to change it to trig. It actually looks just like that, but we'll change it to trig. Doesn't really change how it looks, so. And so at the number -1, we could cheat because you'd think that's where it might have a vertical asymptote, but it clearly does not have a vertical asymptote at -1. But you can see that it is undefined at it. It says error on the calculator, so there's a hole there at -1. So it's a removable discontinuity at x equals -1. Okay, one-sided limits. So on 38, doing this one-sided limit here, as it comes in from the left, it's coming in from the left. It's x squared over x squared plus 4. There is no asymptotes on this because if you try to solve it, it doesn't factor, and there doesn't. X squared is never -4, so it doesn't exist. So there's never a place where it's going to equal 0 at, so it never has any asymptotes. So we can just plug in the 2 on it and get the answer. So if you plug in 2, you get 2 squared over 2 squared plus 4. So 4 over 8, so a half. Then down here, this one factors 2. It factors in the 3x minus 1 times 2x plus 1. And on the bottom, this factors in the 2x minus 3 times 2x plus 1. So at negative 1/2, you can see that cancels out. That one's gone. So what that leaves behind then, 3x minus 1 over 2x minus 3. So at the number negative 1/2, it's a removable discontinuity. So we can just plug in the number 1/2 to what's left here after we removed it. So putting in the number negative 1/2, 3 times negative 1/2 minus 1 over 2 times negative 1/2 minus 3. You would get, when you do the math, 5/8. So the answer to the whole thing is 5 over 8. Properties of infinite limits. Let C and L be real numbers. Remember, C is an x value, L is a y value. And let f and g be functions such that when you have f of x at the limit of x equals c, if it's infinite, and the limit when it approaches c of g of x equals a number, some number L. So L is a number. So if you had f plus g, and f here was infinite, plus g, which was a number, well, it's going to be infinite, like they said. Here, if you multiply them together, the two of them, a number times infinity, you've still got infinity. Here, if you do it again, this time if L is less than 1, so if it's a negative L times infinity again, you're going to have negative infinity. And then, which they had, and then on the next one, if you have g of x, which is L again, divided by f of x, which was infinity. No, did I get that wrong? No, I did it right. So you have a number over infinity, that's going to be 0. We've talked about that with horizontal limits. So if you divide by infinity, it's 0. So down here, we have f, which is negative infinity, plus g, which is the number 3. Well, heck, that's going to be negative infinity still. And then f, negative infinity, times g, which is positive 3. That's still negative infinity. And then g, which is 3, over f, which is negative infinity, that's 0. There's no negative 0, so it's just 0. All right. See you again.